Hey guys, welcome to yet another fun-filled day of adventure and fun in the world of erosion and deposition. Today we're going to start running water. That's probably going to run the rest of the week. Just a couple quick points on that. I believe that we will be having our test next Tuesday. So that would be Tuesday, today's the 4th, so that would be the 12th of May will be your test. Either Tuesday or Wednesday of next week. We have office hours today at 1 o'clock till 2:30. So if you have any questions, feel free to come by. You all should have gotten your projects. I hope you enjoyed the video. If you did, leave some stupid comments about how dumb it was. I know it was dumb. But I hope you guys all enjoyed your video. You should have all gotten your projects, your topics. You should understand what you're doing. If you have any questions on that stuff, that's what the office hours tomorrow will be. Or any other time, feel free to email us and ask us any questions that you may be having. Otherwise, let's start with the running water. Let's go. All right, so when we're talking about running water, once again, we're getting into stuff from like the water cycle. So this should be all stuff that we've talked about. So running water, we're talking about water that's moving on its own, usually caused by the force of gravity. Okay, now running water is always going to begin as what we call sheet flow. Okay, and I'll show you a picture of what that is in a second. Now, this could either come from direct precipitation and runoff, so it rains, it snows, or something like that, and then the water runs along the ground, or melt water from a glacier or an ice cap or something like that at the top of a mountain. Eventually, this sheet flow, which is what you're seeing in front of you right now. So what is sheet flow? Sheet flow is basically, it rains and you just get those layers of water that move down the slope. Okay, think about what, when we have a really bad rainstorm, your driveway has this where it just has the water comes down and like a big sheet. Eventually, those tiny little, that huge amount of water kind of goes into tiny little channels. We call these rills. Okay. And that's what you're seeing in front of your screen right now. These are tiny little channels where the water runs. It always runs down in certain ways. Those rills are going to combine to make what we call gullies. And eventually those gullies are going to combine to make what we call streams and eventually rivers. So this is all what we call drainage. That's what happens when it rains. That is always going to happen. And while this is happening, that water that's flowing along the ground is going to be picking up sediments. It's going to be eroding the ground beneath it. So not only is the water moving, but it's also carrying little bits of the ground with it. And the more water you have, and the faster that water goes, the more stuff you can carry. Okay, so once you have this runoff happening, this sheet flow happening, the rills and the gullies and all those things, you create what we call a drainage network. The drainage network is basically the land that supplies water to a stream or a river. So basically it's all the land that gets these sheet flows or these rills or these gullies that'll eventually collect that water into what we would consider to be a stream. Okay, the drainage pattern that you get depends on the type of rock that you have underneath you, as well as the amount of streams and stuff like that. So basically what you're looking at is all the stuff that's getting dumped into this larger body of flowing water. Now, the picture that you see before you actually shows a bunch of different drainage patterns. It gives you the drainage pattern from something as large as the Mississippi River. So if you look in the upper left-hand corner, you can see that large green mass. That shows you all the rivers that contribute to the Mississippi being the largest river that we have here in the United States. So all of those rivers touching all of those states drains into the Mississippi. Now, when you look in the middle section, you see there are smaller little rivers. There's the Missouri River, the Arkansas Red and White, the Ohio River. All of these are going to contribute. So this is why you can have rivers contributing to larger rivers. And inside those, you have to imagine you have streams and stuff like that. And in fact, if you look, you can see that there's a section of the map that's in very dark green. That's Yellowstone National Park. And they actually show you the Yellowstone River, which you can see here. Okay, and how it has these other rivers that flow into it from different places. So these drainage patterns are not isolated things. There's a lot of interconnectedness. This is one of the reasons why we have to be so careful with our water resources, because if you dump something in it or you pollute a river in one part of the United States, that can affect a huge swath of the rest of the United States, and not only the United States, but other countries as well. So we have to be very careful with our water resources. If you have an area, all the little streams will eventually collect into something. That pattern can be different. We have different patterns. We have what we call the dendritic pattern, the radial pattern, the rectangular pattern, and the trellis pattern. Okay, and if we look at them, okay, these are your different patterns. So your dendritic pattern looks like this. Easiest way I can explain it is it looks like the branch of a tree. Okay, and so what basically happens with this is when you have bedrock that's roughly the same, the water is going to wear away at it, And what you're going to get is this branching. So you have your little tiny streams here. They collect into bigger streams. Those bigger streams, two of them are going to collect into a slightly bigger one, and et cetera, et cetera. So the dendritic pattern happens on bedrock that is roughly the same, and it looks like a tree branch. The radial pattern, which looks like this here, okay, happens when you have melt from a glacier or ice cap at the top, snow cap I should say, at the top of a volcano on a mountain, okay, and it runs downhill, and so it radiates out. So you see how all the water, see how the arrows are pointing out? So the water is all coming out from that central point. So that tells you that this central point is higher and that this is all going downhill because water always forms downhill, okay? And then we have the rectangular pattern, which is here, okay? And this is gonna happen when you have bedrock that has like clear cut, what we call jointing, where it looks literally like it's fit together, but like as if it was bricks or something like that. And so you see this pattern here. So you have a couple of rivers, not a whole lot of streams or things like that, tiny little branches that are going to collect into the larger, but they're going to tend to form along the pattern, along the joining or jointing pattern here. And the last one is what we call a trellis pattern. And if you look at this one, okay, a trellis pattern happens when you have areas that have a weak resistance next to areas that have very, very high resistance. And so what's going to happen is the water is going to eat away at the areas that have low resistance and not going to do much. And so what you're going to end up getting is a series of rivers. So see here, you have a river here. The water is going to drain into that river. But this piece of bedrock is relatively resistant. And so it's going to give you an area where the water is not going to be able to break down. So it's going to run off of here and into the place where the river can actually cut. And then you get nothing here, and then the same pattern happens here. And so you can sort of see it in this one right. All right, so if we look at a stream, streams move, and the water that they move inside of them, and therefore the eroded materials that they move inside of them, all move because of differences in potential energy, kinetic energy, and gradient, okay? And so when you look at it, most streams are going to follow this pattern. Okay, in order for a stream to flow, it always has to flow from a higher elevation to a lower elevation. We understand this is how water works. Water always goes downhill. So typically you'll have a lake, or you could have a glacier. Some source will be up here at a higher elevation, and all rivers eventually, the stuff they carry, well, I should say not eventually, but mostly empty out into the ocean or the sea or something like that. And so if we look at this is what we talked about before. When you have water up here, the water up here and anything that happens to be carrying, okay, is going to have the greatest amount of potential energy here. It's going to be moving usually the slowest at the highest elevation. As it goes downhill, remember we talked about it, it starts to lose potential energy, but it starts to gain kinetic energy. So what happens? As the river flows downhill, it's going to be moving the fastest. So rivers move faster as they're going downhill, right? As the steeper the gradient is, the faster it's going to go. Also, the steeper it's going to go, the more erosion you're going to have. So if this was like this, you're going to have a lot of erosion. If it was a little bit flatter, you're not going to have as much. And if it was super, super steep, you're going to have a ton. That's why something like a waterfall has a ton of erosion. Whereas by the time the river gets down to here, what happens to the gradient? What happens to the steepness of it? It flattens out, which means you're not going to get as much erosion here. And eventually that river is going to hit the ocean. And when that river hits the ocean, it loses speed. It slows down. And anything it happens to be carrying gets dropped off. So here you're going to have, where it's super steep, a ton of erosion. And here where you get to the ocean, you're going to have a ton of deposition. Okay? And so when we're looking at this, we always have to realize that streams are always this balancing act between erosion and deposition, constantly. They weather it away, they carry it away, and then eventually they drop it. All right, so when we talk about the speed and the amount of water that's being carried in a river, which is what we just talked about, there's three main things that are going to affect that, affect the speed of the river. First one is gradient, which we just talked about, right? The steeper the river is, the faster the water is going to go. So something like a waterfall, like I just said, is going to be the fastest. And something that's on a very, very flat land is going to be incredibly slow. Okay, good. So we did that. The second one is what we call stream discharge. And then the third one is channel characteristics. So for what we're going to talk about now is stream discharge. When we talk about discharge, we're basically talking about the amount of water that is moving past a certain point at a certain period of time. Okay, how much? What's the volume of the water? Okay, if you have a lot of water moving past a certain point, well, that could mean, and that probably means, that your river is flowing relatively fast. Okay, if you've got millions of gallons of water moving past a certain point, your river probably has a pretty decent speed. Now, we also have to keep in mind what's the size of the river, because if your river is miles wide, you should have millions of gallons of water moving by. And if it's only a couple 100 feet and you have millions of gallons going by, that is ridiculously fast. So that's going to be quite important. All right, and so now the next thing that's going to affect the speed of the river is the channel characteristics, specifically what we refer to as the profile. The profile is basically the cross-section. If you would take the river and chop it in half and look at it directly in front of you, like if you sliced an apple in front of you, what would you see? Okay, what does it look like? Now, the typical shape of most rivers is they're going to tend to be V-shaped. They can round a little bit as they get older towards the bottom, but younger rivers tend to have a sharp V shape. As they get older, they tend to get a little bit wider, a little bit flatter. The other things you're talking about is, well, what's on the bottom of the river? Is the bottom of the river a very durable material? What's the bedrock like? Is it a lot of sediment? Is it not a lot of sediment? Those are all properties. If you have a ton of sediment on the bottom, that's going to mean that your river can't flow nearly as fast. If it tends to be more streamlined, then it's going to tend to form a little bit faster. So when we're looking at the profile of a river, you can actually see the profiles in front of you right now. You see how it has this deep shape, okay? And the water is going to flow in this. You can see the one in the middle particularly has that nice V shape, which is typically what we look for when we look for like river valleys or things like that. The rivers on either side of them might be a bit older. Now, when we look at a river valley and we look at water flowing through a river, we have to pay attention to the speed of the river. Now, the water as it moves through the river is going to not actually travel at the same speed all over the place. Why? Well, because as the water rubs up against the bottom of the river, that's going to generate friction. It's going to slow it down. The same thing with the stuff on the outside. So the highest velocity for a nice straight channel is always going to be in the dead center. The fastest water is always going to be in the center as long as the river is going straight. Now, once the river starts to bend and twist, then we're going to run into some problems. So, for example, when a river bends, we call that a meander. Okay? It means it makes these S-like curves. Okay? Now, when it makes these S-like curves, it's really important that we know how fast the river is going and where. So, if you look at the picture in front of you right now, okay, you will see a bunch of lines that say A and then A prime, B and B, and C prime. And so if we're looking at this picture, we got to explain what's going on here. Okay, well, if we're looking at it at A, the river's flowing straight, so the fastest water is going to be in the dead center. But once we get to B, we're into these curves, B prime line. B prime is the B with the little apostrophe next to it. Okay? When we look at this, I want you to imagine running a race. Okay? When you're running a race, where do you always want to be? You want to be on the inside lane. Why? Because the inside lane is actually the shortest distance around the track. Okay, and since it's the shortest distance, technically you don't have to push as fast. Well, the same thing is going to happen in a stream. When the river goes through this first curve right at B and B prime, the water that's going around B prime, B with the apostrophe, doesn't have to travel as fast. Okay, and so what happens when water slows down? Well, when water slows down, you're going to do more deposition. You're going to drop stuff off. Okay, and so your water is going to be flowing slower there. Whereas B, that's the guy or the girl all the way on the outside lane. In order to try to keep up with everybody else that's running, that person is going to have to push themselves even harder, which means at B, you're going to have the water flowing at its absolute fastest. And so what happens there is when the water is flowing fast, it's going to eat away more at the rock that's there and the material that's there. And so at B, you're going to tend to have more erosion. So what ends up happening, since you're eating away at the ground, B is going to tend to be deeper, whereas B prime is going to tend to be shallower. Okay? Because you're dropping stuff off there. And so that's why you end up, if you look at the right side of the picture, you end up with B being a deeper hole and B prime kind of being a little bit more shallow. Why? Because you've dropped off a bunch of stuff there. C is the inverse. At C, you get the opposite process happening. Okay? When you get to C and C prime, it's a flipped over image. Now C prime is where the fast water is going, and C is where the slow water is going. And so that's going to give you a very different view, and that's why the image looks slightly different in that picture. All right, guys, so that's it for running water part 1. We will continue this tomorrow. Please make sure that you are studying, taking notes, studying for this week's quiz and next week's test. There is a quest up on Test Wizard. It is due next Monday. Make sure that you do that. And once again, we will be having office hours tomorrow. All right, guys, see you later.